Stoiciometry, what? By Maria, Clarence, and Isaac. So we're given the compound polytetrafluoroethylene. I probably said that wrong, but I am trying. Which is also known as Teflon, which is a type of plastic. The chemical formula, oh my dog's crying. The chemical formula is C2F4 parentheses 2. And as you can see here, the equation is already balanced. Yay, what? So we're going to start with 5 different examples of stoichiometry, which is mole to mole conversions, mole to mass conversions, mass to mass conversions, and then limiting reactants and percent yields. So we're going to start with moles of reactants to moles of products. So as you can see here, how many moles of C2F4 parentheses 2 can form from 8 moles of C2. So first, we must start with the balanced equation, in which we took the liberty of writing it in between everything. Second, convert units of the given substance to moles. Third, using the mole ratio, calculate the moles of a substance yielded by the reaction. 4, convert the moles of an unwanted substance to desired units. So as you can see here, we did that. We used the mole ratio, and then yeah, basically it. For the next one, we have moles of reactants to mass of products. What's the mass of C2F4 parentheses 2 if we have 4 moles of C2? So, and also when you're doing conversion, double conversions, all those, you must what's it called? Oh, sorry. You must cross them out so you know what you've already done and what your answer you would usually end up being. With like here it'd be C2F4 parentheses 2 as in here. And so basically for moles of reactants to mass products, you would have to get what is known, determine the mass of the product, convert the moles of C2 to moles of C2F4 parentheses 2 using the mole ratio from the equation, and then convert moles of C2 to grams of C2F4 2 using the molar masses of the conversion factor. Next up, we have mass of reactants to mass of products. So with almost every equation, you must start with the balanced equation. And for most of these, we don't have the balanced equation written on there, but in the second slide, we have already established the balanced equation. But for this one, we have it there. And you have to get what is known, write the balanced equation, convert the known masses of a reactant to moles of the reactants, use the mole ratio to relate moles of reactants to moles of the products, use the molar mass to convert from moles of products to the mass of the products, and that is basically it. And as you can see here, and the way you get a molar mass is you combine all of the C4 and F8 together. So C4 would be 12.011 times 4 because you have 4 carbon, and then fluorine would just be times 8, and you combine them both to get with the molar mass, which you would here is 20.028 because you're dealing with grams. So you start with like 18 grams of that, and so you have to start with the grams of all of it. And then you would get the molar ratio, and yeah, that's basically it. So then we have limiting reactant. So limiting reactants are a bit more difficult than the other 5 that I'm about to show you, and that is because they usually consist of 2 questions. So the first one is A, determine the mass of C4F8 if 25 grams of C4 and 50 grams of F8 are combined. B, how much of an excess reactant remains after the reaction stops. So this one is more of a more than 2-step problem. It's more of like a 1, 2, 3, 4, 5, like 5 steps of the problem to answer both. And so the way you would do it was you start with basically what is known first, and in the equation it tells you 25 grams of C4 and 50 grams of F8, in which you write here, but you want to know what they are both combined. So you have C4 plus F8, and then yield C4 F8, and you want to know the grams of it. So basically all you would have to do would just get the balanced equation for the chemical reaction, of course. Then convert the given formula into moles. So as you start here, you have the given, then you convert it into moles. Second, using stoichiometry for each individual reactant to find the mass of the product produced. So you start from moles, and then as you have moles, you start getting the what's that thing called? The mole ratios, as you can see here. Oh, my dog's crying, I'm sorry. You have the mole ratio, and then so you start like that, and then you would get fluorine's number, which is 0.3289 moles of F8, and you would times it by 1 mole of C4F8, and you would just get 0.3289 moles of C4F8, and then so basically the writing is kind of confusing, but you go from here to here to here and then down, and then you would go to here and you would times the number you get here by the molar mass, which is 65.7 grams of C4F8. And then we have a part 2 of this, of course, because of the next problem, and that would basically be the answer. That's what they are both combined. For the second part, I will just repeat the question to you. How much of the excess reactant remains after the reaction stops? So for the part B, it's a bit more different. You have to convert the given information into moles using stoichiometry for each individual reactant to find the mass of the product produced. The reactant that produces a lesser amount of the product is a limiting reactant. The reactant that produces a larger amount of the product is the excess reactant. So this would be the excess reactant. As you can see here, so you go from the moles, and then use stoichiometry, and then go through all the what produces what, and that is basically it. And at the end of this video, I will be leaving more of a tip and explaining what each of these, what a limiting reactant is, what is mass to mass, and all of that as well. So then we have percent yield. So percent yield is a bit different than the rest, because it is not as long as a process, but it is way more numbers. So for percent yield, you have to have the theoretical yield divided by the percent yield, which is also known as the actual yield, and timing it by 100. And if I pause, it's because I try to focus. So basically, you just times that by 100, and that would give you the percent yield. So for here, we have a given mass of Teflon of 0.500 grams of C2F4 parentheses 2, and then the actual yield, also known as percent yield, 0.455 grams of C2H3F4 parentheses 2. And then the way you get the molar mass, as I explained before, is just combining all of the C4F8. And a little heads up, when you see a number times 10 negative 3, it just means that this number originally it will have more decimals per se. So just in picture 2 zeros and a decimal, and since it's a negative, it'll be going to the left. So it goes from the decimal and then 1, 2, 3 with two zeros I meant. And that's how you get the moles from that. And then basically the actual yield is the actual amount produced when the experiment or reaction is carried out. The calculating of the percent yield, first we need to calculate the theoretical yield based on the limiting reactant. If there is more than one reactant, this is the reactant that produces a smaller amount of product. And as you can see here, this is from all the math that we have. That's not your final answer yet. So this is where I meant where you would get the actual yield, also known as this is percent yield, actual yield, theoretical yield, and then times it by 100. So it's the actual yield divided by the theoretical yield times 100, getting you 35% C2H3F4. And this is our third take. But I also wanted to say that for percent yield, we had to change our balanced equation just for the purpose of percent yield, and we had added H3 and oxygen for oxygen. But usually you have to write down what is known and what is unknown for what you have to find. So thank you, and thank you for lending me your time, and At the end of this video, I will have a few more tips and a bit more of an explanation for each of these, so you know exactly for and what you have to look for. Thank you.